So, good morning everyone and women. I welcome you to the second day from our lecture series. And already, nice idea. Could be this one. We will start after we have heard yesterday about data fusion and some ideas how one should, or which one should consider if one thinks of building a multi-sensor network. No, that's a presentation from yesterday. Probably not interested to see that again. And off you go. No, my second presentation will be focused again more on the hardware aspects of a sensor network one should consider if one has the possibility to design it from the scratch. And one thing one big issue is synchronization. Even nowadays, this is essentially, if you travel a lot, you have to synchronize your clock with a local time, I realize. And you're laughing. Was so obviously my fault in Halifax. So, something about the coverage, localization, and a good way to get knowledge of your system, also on a monostatic system, is to investigate the ambiguity function. And if you want to know how good you are in determining the position of your target, then one way to do it is to determine the position dilution of precision, which is a well-known way in the global satellite navigation system. Now, synchronization takes seconds until it appears there. In the earlier days, there was not really a need for synchronization. Every city has its own time, so let's say called solar time. And if you want to make business with the next city, should be not a problem. So deviation was only between the cities by several minutes. Now, during the transportation pickup, there was some demand in synchronizing the times, especially with the railway, when you are able to overcome distance of several hundred kilometers in less than a few hours. So you are not very used to have different times in between. And this led to huge problem, and every country solved this on its own way. So in the first half of the 19th century, every nation has its own time zone, and this was mainly determined by the capital of the country. And this leads to very different time zones in all European countries. And in Europe, this is not a very big problem as the countries are small. But if you have a problem to make a time schedule for railway systems, which is in Canada, you will get a little bit problem. You will not be able to argument to all citizens that this huge country has only one time zone and they have to live with it. So that was a real problem for Sir Sanford Fleming, who proposed to split up the country in several time zones. And not only the country, so he goes one step further. The whole world was then divided in time zones, approximately every 15 degrees of latitude. So it should be, but looking at Wikipedia and the time zone map, you will recognize that that's not always the case. The funny things are there. You go, for instance, from Spain to Portugal and you lose 1 hour. Or from Reston to Halifax. And if you don't adjust your time, you will just miss your colleagues. So you have to synchronize. Still nowadays. If you think of doing it in a radar network, you have to go a little bit more. You have not only to synchronize in the day, in the hour, you have also to synchronize in the seconds, and even better, depends on your demand. If you want to know when the transmitter is firing the signal, you need the time synchronization. Or if you have a turning antenna and you know the speed of rotation, or you have a time schedule, you must exactly know in which direction the transmitter antenna is pointing, so you would be able to pick up any echo. Also, there's a synchronization need in the frequency, so you are looking at the same bandwidth and have no mismatch. And if you are interested in doing coherent signal processing for pulse compression or for Doppler shifts, then you have also synchronize or have a stable phase relationship between transmit and receiver node. How can we achieve this? There exist several possibilities. Depends on what is your demand, what is your budget you are allowed to spend on it. One way would be, or the first way, use stable oscillators. This can be very high stable crystal oscillators, or if you have some money more, you can go for an atomic clock. But even using two very stable clocks, atomic clocks, you will recognize they will drift away over the time. Even just looking for 1 day, these clocks show a significant drift. Now to improve this, you can do direct synchronization. If the nodes are not too far away, you can connect them with a cable or with an optical fiber. Or one can also think of, if there's a line of sight, use a direct communication link for transferring the reference signal from one node to another. But one has also nowadays the possibility to use an indirect synchronization, which means you are using a third reference clock to synchronize the transmit and receive node, which can be a GPS system or the upcoming Galileo systems. Both systems provide a time, and the receiver gives you pulse per second, so you are able to synchronize this on it. And you see, even if you are choosing a very good crystal oscillator, which will come back has a very good behavior in this region, in the phase noise region. Here you see over the time the variance of the time. You will have over a day a very dramatic drift between two nodes. Even with rubidium or cesium clocks, they will go away. To overcome this, I should mention another problem with a bistatic system is not only the local clocks can drift, but we can synchronize now using cable, transferring pulse per second. One has to look on the phase noise, which is in this table the lower part. The phase noise describes the behavior of the frequency just a little bit besides the center the carrier, and it's denoted with dBc, dB below carrier, and the other number here is the offset frequency of the carrier. So if you need a very long integration time to determine the Doppler shifts for reflected signal, you need in a bistatic system very low phase noise on both sides. In a monostatic system, the phase noise shows a very good correlation as you are using the same oscillator to generate the transmit signal and to generate the reference signal. So the short time period of several seconds, even then the generated reference signal shows significant correlation to the received signal. This is not the case in a bistatic system where you have a transmit node which generates from one reference clock the signal which will be transmitted, and on the receiver side we have to generate somewhere your reference signal for doing a correlation. This will be generated using a different clock, so there will be no link, except if you're using cable and transferring the reference signal from one node to another one. But this depends on the distance between the nodes, not very feasible, so you have also to look into the phase noise, and a very good phase noise you can gain with a special cut through the crystal and special design of the housing, and also temperature compensation has to be performed, so you are able to have a very low phase noise and can do a very long integration between two nodes. And unfortunately, these low phase noise sources show, in comparison to atomic clocks, not so good long-term stability. So if you want to do the performance over 1 day, 1 week, and so, they will drift a lot. You see, the factor of 100 is between the GPS system and this BVA cut oscillator. And is there a possibility to combine both systems, have a low phase noise reference and a long-term stable system? That would mean that you are able to combine GPS and the crystal oscillator. And this is done. You can buy for several thousand euros such unit, or you can do it by your own. You have to take a GPS receiver which delivers pulse per second signal, which is unfortunately variable with a variance of several hundred microseconds. The variance of this signal, but over the long term you will get a very stable system. So this pulse per second signal has to be compared with the pulse per second signal generated from your reference, your local reference, which we normally 10 Hertz signal. This is then down divided compared to the pulse per second, and over a low pass filter or matched filter, control signal is generated so the crystal can be steered into the right frequency. Due to this very long peak, very low frequency of the closed circle, the PL circle, you are able to obtain the low phase noise of the crystal oscillator and the very good long stable stability of the GPS receiver. And what is the demand is quite easy, depends on your update interval and your time stability you need it. And if you're using a third clock to synchronize transmit and receive nodes, you have to take into account that your stability has to be a factor of 2 higher than which is given by this small formula. For instance, if you have an update rate for at 0.1 microseconds, time deviation is allowed with 0.1 microseconds, and update interval of 10 seconds, you need time stability of this number. And remember the table which we have just seen. This can be easily achieved by the crystal oscillator, so there's not a big demand. This change a little bit if you need coherent signal processing like Doppler or MTI, then you have also to look into the stable phase. And here is given the allowable phase deviation over the coherent signal processing time. And again, it appears the reference, the frequency of your center frequency, the update interval, and then you will get your demand for the phase stability. And here you are coming at a point where it's critical is to use a crystal oscillator, so you have to go a step further and combine GPS, the long-term stability, with the short-term stability of a crystal oscillator. Now, an example what I have done a couple of years ago was to use a cheap GPS receiver here, temperature stable crystal oscillator, and placing 2 units just side by side, having 2 antennas nearly co-located. I was able to attain a time deviation of 50 nanoseconds over 60,000 seconds, so it was the whole night running, and I think it's very good, 50 nanoseconds deviation. I was able to obtain an update of this GPS receiver, which shows a significant improvement in delivering an accurate 1 pulse per second signal. And doing this and looking into a smaller range of only 3,500 seconds, you can see it was possible to reduce the variance dramatically. And if you are thinking of that you have an only coherent signal processing time of a second, you should be able to have a deviation of less than 1 nanosecond between 2 stations. And this is quite good. Another point one has to consider for bistatic network is that if you're using a high gain antenna with a small beam, that both beams are overlapping, so you have a common area which one sees and observes, and this depends on the geometry. One can easily think of that this is just pointing in this direction, and the transmitter pointing in this direction, and the receiver, that the shape of the common coverage will change. So we have dependence from our minimal range and maximum range we can see. To adapt the system, one can think of to shorten the transmit pulse so it just fits into this common area, and then we can increase our pulse repetition frequency, so we have a higher update rate, for instance. But unfortunately, with a shorter pulse, there is we are able to determine a higher speed of our target, that's sure, but unfortunately we are not able to determine with a better resolution. We will lose the resolution, the ability to determine it exact, but we have a higher ambiguity range in the speed. Also, if we have two transmitters and one receiver, and they're emitting similar waveforms looking into the same area, we will have problems with the Doppler shift, as this different bistatic constellation. The same target will show different Doppler shifts depending on which transmit waveform one has to look. This can be a problem on the receiver side if you cannot distinguish between the transmit signals. To overcome this problem, one can think of to use a time separation, so only one transmitter is emitting his energy, and then if the energy has just disappeared, the second one emits his energy. Another possibility is to use orthogonal waveforms, so the receiver is able to distinguish between the waveforms and can say from which transmitter it comes. Also, another possibility, which is sketched here, is to use a separate range interval, so you will be able to know and to determine or to correct the Doppler shift in a right way. Another possibility to get more knowledge of your system is to determine the ambiguity function, which is a response of a matched filter. As a reference for this matched filter, we are using the time delayed and Doppler shifted reference transmitted signal, and it's a very good way to investigate if the constellation is okay, if the waveform is what one expects, if it's possible to determine the needed Doppler shifts, and normally this will then display in a range Doppler shift plane, but it's also possible to display it in a delay and speed of target plane. And for monostatic systems, for instance, you will see that the ambiguity function for a single rectangular pulse transmitted has such a form. In this direction it's the range, and in this is the Doppler shift, or the speed of target. And this changes dramatically if you are using 5 rectangular pulses for your signal. So working over 5 pulses, you will see there is a little bit spiky ambiguity function. in it. And as bistatic geometry is a simple linear relationship between the time delay and range is no longer valid, one has to expand the ambiguity function for using it in a bistatic system. And this leads to the following equation, where we have to take into account the actual position of the target and the hypothetical position and the hypothetical speed and direction, movement direction of the target. And going further into the calculation for bistatic systems, I will show you that the shape of the ambiguity function will change dramatically depending on where the target is in the geometry. And for the following simulation, I assumed that Gaussian-shaped pulse, as described here, is used for the system at the center frequency of approximately 15 megahertz. And for a monostatic system, one will see a very nice head. One is able to determine in range and speed or Doppler shift with the same accuracy. This changes if we have transmit and receive nodes and the target is approaching the spaceline. The resolution and range changes dramatically, and in Doppler shift also see the ambiguity function in the range and speed is no more this nice head, the Gaussian shaped head. And what will this shape be if the target is approaching the baseline? You will see what I already mentioned yesterday. You will not be able to determine your target. You will have no Doppler shift as the target crosses the baseline, and you will also have no possibility to determine where it is, as the signal from the target, the echo, has no time delay. And this is also clearly visible in the ambiguity function. Now, for monostatic, bistatic systems, next step for multistatic systems, we have to use the following 3 steps to calculate it for more than one bistatic pair. We have to do it for all bistatic pair and even for monostatic pairs. Monostatic is just a special case of the bistatic configuration, remember it. Then we have to calculate a weighting factor according to the received signal intensity, and then you have a weighting function, and finally we have to sum up over all transmit-receive pairs in our network. And then we have the final multistatic ambiguity function. In this assumption, we assume that we have a fully coherent network, and the waveforms we are transmitting are similar, and the RCS of the target is similar to all radar bistatic pairs. To investigate, the simulation was done with transmit and receive nodes lying on one plane and separation or baseline of 10 kilometer. The target is flying parallel to this plane with a speed of 600 meters per second. And as we are going into the 3-dimensional space, we have to take a vectorial approach to determine the delay and the Doppler shift. And if you are thinking of a 2-dimensional case, you will have such an ambiguity function, and looking into the cuts in the range profile and in the Doppler shift, you will recognize that it's not possible to determine the Doppler shift of the target, so the speed of target is not clearly determinable. And if we are assuming that the target is flying at an altitude of 20 kilometers, this ambiguity function changes dramatically. It improves, one can say. It's possible to determine the range very accurate. Also, the speed of target is possible to determine. This will change dramatically if the plane is not at an altitude of 20 kilometers. If we assume it has only 4 kilometers altitude, you see finally the range resolution drops, but still one can determine there is a target, and but it's not really possible to determine clearly with a high confidence the speed of target. That also leads to the assumption that the target, the position of target to baseline is a critical part in a bistatic system. So, if possible, and you design your system, you should select a configuration where your target is far away from your baseline, so you will be able to distinguish it correct. Another problem, I mentioned it, I think yesterday, is from my point of view a real challenge for a bistatic system, that you have, in comparison to a monostatic system, a very strong direct signal. You have also some multipath signals which are similar to a monostatic system, and you should have a reflection, the echo from your target. Maybe a moving target, maybe also have a stationary target. But the biggest problem is the direct signal, and why is this the case? As the attenuation of this signal is only by 1 over the squared baseline in comparison to each multipath or reflected signals, which is reduced by the radar cross-section. For instance, for a small target, 10 square meters, and the squared distance of the transmitter to target and the target receiver, and which is in normal case much larger than the baseline. So there will be a lot of amplitude, power difference between transmit signal and echo. This can easily calculated with a direct signal noise ratio. You have to take into account also the antenna gain pointing towards the transmitter. No, if you're taking the transmitter gain pointing towards the receiver and vice versa. And here you have only the baseline, the square baseline. For signal to direct signal power ratio, we do have then following equation with baseline between transmit receive nodes and transmit and receive distance, and again the radar cross section, which reduce further the amplitude, and also you have to take into account now the antenna gains pointing the top point here pointing towards the targets of transmit and receive. How does that look like if you have two omnidirectional antennas? It means a single antenna on transmit and receive nodes. Both have such a characteristic illuminating the room equally. Then you have a signal or signal direct signal ratio, which is depicted here. You see it's like the normal signal to noise ratio, except that you have already at this place a demand of more than 100 dB dynamic, as you have to deal with the direct signal. To overcome this is one possibility to use, for instance, an antenna array. I have used here or calculated a 9-element array, which has a nice gain antenna beam in this direction. And if you are able to shift a null of the antenna beam, which is for instance here, towards the transmit station, you can improve your system performance by reducing the direct signal. Another common way is to use only a high gain antenna on the receive side, which points in this direction, and have a small antenna as a reference for the reference signal, which points towards the receiver, and this also helps by let's say 20 to 30 dB. It depends on the antenna you are using on the receiver side and looking into this direction. So keep in mind, if you are working with omnidirectional illuminators, the direct signal will be the problem you are faced with. Now, we are able to determine from a bistatic system the bistatic range from the delay between the direct signal, for instance, and the echo signal. Or if we have a good synchronization, we know when the transmitter is firing the signal, we can determine in this way the time delay. We are able to determine the Doppler shift. Also, we are able, if we are using high gain antenna on the receiver side, the angle of arrival. And if we are doing this for more than one transmit receivers pairs, we can easily determine the position of our objects which are moving or in certain state or in ground. And this it can be done by easily multilateration or by a parameter estimation. The easiest way, and I think well known, and also it's performed every day if you're using a GPS system, is multilateration, which is also sometimes called hyperbolic positioning. You have the time delay of several transmit-receive pairs, and you have only the time delays, and each receive-transmit pair gives you such an ellipse. If you're thinking in a two-dimensional case, and if you are like to think in a three-dimensional case, it will be such, let's say, American baseball like. And if you add some more, you will see that the intersection shows the possibility where the target is positioned. And if you have three measurements in the plane, you will end up that only in this case where all ellipses have a common place, there is your target. And again, if you're using it just in a two-dimensional case, you need a minimum of 3 measurements to determine your position. And if you are interested to see where is your target in the space, you will need one more transmit-receive pair. And this is very simple for a single target in the system, but if you have many targets, it's a little bit problematic to eliminate all ghosts, as we have a very large set of combination, which is, for instance, here the case. Paul Holland from NATO C3 has performed a trial with one receiver in the center and 3 transmitters and several 9 targets in this observation area, and you will get a lot of ghosts which all have to be eliminated. And one way to do it is to make tracking of your system, so taking the time history into account. This is a quite easy way to eliminate the ghosts. So you see, sensor fusion and data tracking is essential also for a multi-static system if you have a couple of more targets than one. To improve the systems, you can add some more transmit-receive pairs and do also some averaging for the time delay of arrival. And if you are interested in how to improve your performance, you should carefully select the antenna and sensor geometry of the transmit-receive systems. Also, the timing accuracy of the receiver system is a crucial part. You have determined the time delay accurately, and also the frequency synchronization of the transmitted signal with the received signal has to be done in a right way, as diffraction of reflection changes the phase of the signal. And also the bandwidth of the emitted pulse is one part which goes into the accuracy. If you're relying on a direct signal, as the lifetime of the pulse determines the starting point of your clock to determine the time difference of arrival. Another way is to determine the position using the parameter estimation. This is a formula which is valid for your receiver signal. It will have complex reflected amplitudes due to the reflection at the target. It will show time delay, and also if you're looking at a coherence network, the carrier frequency has a phase, the carrier phase, because it has to be taken into account. And this, the parameter can easily be determined, the time delay. This can be done for non-coherent or coherent sensor network. For a coherent network, you are able to determine the phase difference in the carrier frequency. In a non-coherent system, this part is not available. Parameters can be estimated using, for instance, the best linear unbiased estimator. If a linear regression model exists, and if the errors have expectations of 0 and are uncorrelated and have equal variance, the blue estimation of the coefficients is given by the ordinary least square estimator. And the best linear unbiased estimator is not very new. It's already described in 1975 by Charles Roy Henderson. Now, the goal of the estimator is to determine the position of the target. Sure, that should be the case. This can be estimated directly by formulating the maximum likelihood estimator as related with this formula, or using this one, so we have determined the position correct. Again, this can be done for a coherence network or even for non-coherence. And clearly, if you're using a coherent network, you have to synchronize your local clocks and to synchronize your reference frequency. And after you have determined the time delay or the time delays of your signals, the target localization processing uses then the well-established multilateration principle As blue needs a linear model, we have to perform a linearization in our geometry, and we are assuming that the target is a point scatterer showing an unknown homogeneous complex radar cross-section, which is for all transmit-receive pairs the same, and using the linearization around the position of the expected localization with this one, we are now able to use the best linear unbiased estimator to estimate the unknown parameters, where mu is the observable time delay vector and epsilon is the noise vector, and the matrix D is the relation between the measured and the observed time delay. Now the estimation leads to the following equation, and we are able to determine the covariance matrix of the estimations by this equation using the relation matrix and the covariance matrix of the errors. And again, the target, if we are have determined the positions of the time delays, we are able to determine the position using the multilateration principle. And looking into the covariance matrix, the error covariance matrix of this estimation, we will see this depends on the center frequency in a coherent, if we are using a coherent network, and on the relative bandwidth of the signal in the system. And the matrix G incorporates all effects of the sensor locations in relation to the target's position. Now, determine the variances in the X and Y. This we are interested in, so we are able to determine the accuracy of a given constellation. So we could easily determine how good is our constellation to determine the accuracy, the position accuracy of our target. And here we are coming to the position distribution of precision, which we can determine from the error covariance matrix. And the PDOP is a common way in the global position satellite systems to map the obtainable location accuracy for a given constellation of GPS satellites. And if the POTP enables to separate the effect of any geometry from the measurement error, so we are able to determine how good is our geometry to determine the position of our target. And for a given linear measurement model, the time delay with noise variance, a corresponding delusion of precision can be defined. And for a two-dimensional case, we are just interested in this is given by this formula, the position delusion of precision, the time delusion of precision. So if you are also have to determine the time, which is the case for any GPS receiver moving here on the Earth's surface, we have also determined the time. And finally, if you have the PDOP and TOP, you are able to determine the full geometry, geometric delusion of precision. With sigma r, the standard deviation of the range estimation defined by the standard deviation of the time delays, and the sigma x and y are the variances of the localization in the x and y axis respectively. The advantage of blue is that its error covariance matrix is given in a closed form, so we are able to determine the PDOP also in a closed form, which is very useful if you have a multistatic network. And the lowest PDOP then corresponds to the most favorable geometry of the problem to observe, for instance, a surveillance area, and the least of 3 sensors are needed to resolve any location ambiguity. And I will now present some results and some simulations, and for these the following assumptions take occur. We have a regular n-sided polygon which is centered at the axis origin, and the target is located at the center.
Excuse me. Is the 3 sensors are required to resolve resolution and location ambiguity? Is it for 2D still, or is it for 3D?
For 2D you need 3 sensors.
For 2D?
Yes. So a minimum of 3 pairs, transmit receive pairs you need, 3 measurements, so forth. You need to determine the position in a 2-dimensional case.
Okay.
1 pair more if you want 1 dimension more. Further, we are taking account that we have n by n transmitting receiver nodes, which are located at the polygon verticals, and we will see the best PDOP which can be obtained is 2 over the number of the sensors in the systems, and it can be shown that this is the lowest obtainable PDOP if the target is inside the system. Also, one assumption for the simulation is that the target shows to all transmit-receive pairs the same radar cross-section, the same reflection coefficients. And if the transmit and receivers are nearly symmetrically placed around the point of origin, you can obtain with 4 transmit and receive nodes each the following PDOP with the best position in the center. And it is for non-coherent, you will see that the best place is around the transmit and receive pair, which is only slowly degradation towards the center and also outside if the target is located outside the system. But this is not the case if you have a coherent network. You will achieve here the best location accuracy in the center with 0.02 for PDOP, and this will be changed dramatically if your target is outside the systems. The PDOP increases here very fast. Why I'm saying nearly symmetrically? If you think of a linear system, for building a linear array using m elements, and you are placing them in a regular way. Normally you are doing it separating by lambda half, then you will get a very nice shape, everything is okay. But if you are interested in having a much larger antenna and you will not fulfill this constraints that the elements are separated by lambda half, you will get high side lobes if you do displacement in a very regular way. So to overcome this, normally you will shift the places of the antenna slightly, so the side lobe of each antenna element interferes, so that in the sum the side lobe will go down. The similar behavior is observable for a coherent network and having a symmetrical constellation. Here you have 2D correlation or autocorrelation for this given setup in a symmetrical way using 4 transmitters and 4 receivers. Non-coherently you will get a very nice shape, but for coherence case you will see a high peak and also very high side lobe peaks, which influence the accuracy of the system. To overcome this problematic, you will normally shift a little bit your transmitter and receivers. Doing it here, you will see the side lobes, I call it side lobes in the 2-dimensional correlation, also change dramatically, and that will help to determine your systems in percent of noise very accurately. So keep in mind, symmetric does not help every time, especially if you want to save money and elements. Another constellation is if you place transmit and receive nodes on a semicircle facing have a target in this direction. Again, the system shown on the left side is non-coherent, and on the right side coherent. You still have been able to obtain the full coherence of all nodes, and you will see that from my point of view that in such an open system where the target is not lying in the system, like in the case before, that the non-coherent system works quite well and has less dramatic change over the range than with coherent systems where you achieve more accurate localization in the near of the transmit and receive nodes. To sum up, multistatic radar network sensitivity depends not only on the radar parameter, one has also to consider the geometry of the systems. Multistatic radar network offers more flexible arrangement of system geometry than traditional monostatic systems, leading to the possibility of configuring radar nodes to form a satisfactory coverage area. And the 3-dimensional geometry has a significant effect on the ambiguity properties, and the degradation of a range and radar resolution shown in the 2-dimensional multistatic radar case can be reduced in a 3-dimensional multistatic radar case. This leads to the assumption that the baseline to target height ratio is a dominant factor. So if you are able to design it in a way that your target will never on the baseline of transmit-receive pair. And maps of PDOP represent a very useful tool for showing the accuracy which can be obtained for a given radar constellation or for choosing the best node locations to cover a given surveillance area. Now you will see this day is an advertising day, so I also do some advertising. I will keep it going. If you are interested in SAR, synthetic aperture radar, I'm the technical chair of the Euler conferences will take place in Nuremberg. It's in Germany. Some say it's Bavaria, not Germany. There exists also some it's not Bavaria, it's Franconia. So we are dealing where it still is, but Google it, you will find it. It will be next year in April. Also, I'm organizing a radar conference, so if you want to learn more on radar or SAR, it's a good possibility. Next year we have it from 13th. Oh, and endless. The whole July, I realize. No, outside there are some flyers. It's 20th July, so it's a week. It's near Bonn, nice city, nice event. This year it will take place approximately two weeks, from 8th to 15th July, but already overbooked. We have very good community applications. We have now nearly 50 attendees for a whole week, starting with social events, visiting Cologne, the cathedrals, Hohenzollern Bridge. You will be there and can feel like Christian Hülsmeyer 100 years ago, and so on. So I have some flyers outside. If you are interested in, you also, if you have some questions, feel free to ask them. Yes?
During your presentation, you have stated that even for GPS case, there is a time drift with respect to the actual time. Do you have any knowledge about time difference between different GPS receivers?
That depends a little bit on the measurements I have performed was a very long average using special and dedicated GPS receiver, which was optimized for timing purposes. You can buy these things. They are also able to determine their position accurate over a very long range, time period, and then they will set up and assume they will be in a fixed mode. So they do not need more to determine their position. They are only focusing then on the time difference. And these units are very good and achieve a deviation of several, I think they claim 50 nanoseconds deviation. But again, if you're doing some averaging and keeping it over smaller range, you can go down up to, as you have seen, less than 1 nanosecond deviation. The long-term drift, that's a question, is it really needed? If two GPS receivers are seeing the same GPS satellites, they will show the same drift. They have the same reference clock. So it's not needed anymore. So they will be kept in time. Yes?
I have a similar question. At the beginning of your talk about the precision of time measures. And time to time we hear that due to earthquakes, the earth rotation gets faster. I think the time gets short in a day. So how do you update your systems or your times or to precise? With all your GPS and things, I guess it works on that basis, right?
Yes.
Is there update issues?
I can forward your answer to the German PTV, which is the official government place for the time in Germany. They can answer probably the question. But again, if you are having two nodes or even more and have one reference from where you extract your time and frequency, it doesn't bother you. You're looking to one reference.
That's a relic.
After the earthquake, yes. After the earthquake, the system will set up again. So, if your reference goes, you will stay to this reference. I think.
During that experiment that you showed us with standard deviation 15 nanoseconds, did you use military GPS receiver or civilian?
Pardon?
During that experiment that you did with standard deviation 15 nanoseconds, did you use military GPS receiver?
No.
Civilian.
Civilian from Motorola, they unfortunately I think they have skipped the production. So still what's it called, OEM modules. You can buy it. Was, what was it? I think 150 euros or less for one module. So not very expensive. So if you have a question to this image, it's the preprocessor or the radar system using between 1904 and 1930. Acoustic radar. Sometimes if you are too early for an idea in the world, like Tristan Hulsmar, he popped up with radar, everyone said, radar, we don't need it. We can look, can see, and we can hear, we doesn't need it. So the idea vanished from the plane, and they came up with these things, and you can look up, Google for acoustic radar, you will find this is a small version. There are also bigger ones available. Just to listen for the audience, no, for the airplane. But it was unfortunately not very successful. They came up again. Yes?
It seems the GPS is the key for synchronization. What's your opinion about without GPS synchronization, like the network? Without GPS.
Without?
How is synchronization, the systems?
Depends on how much money you have. All a question of money. GPS is cheap, nowadays cheap, everywhere, and it's good for timing. If you need a very high precision, there's you have to look into the astrophysics region. They're doing synchronization via dedicated communication links via satellite in a two-way link. So they have the station on the ground going up to the satellites and again down to the receiver station. There the signal will be returned and retransmitted. So they know the two-way delay and can correct the signal. The same also to the second station, and they changed over this way the signal and receive also their own signal. And then they can get very accurate and very good phase stability, which is needed to do astrophysics over the Earth. You remember they're using very huge satellite antenna looking into the space, which is just spread over the Earth. And they're doing it in this way, the synchronization.
If we have a ground lines, can we use a network synchronization?
You think of Ethernet?
No. Close fastnet.
Fastnet, yes, but can you be sure that the package with the time information arrives in the exact time? Especially if you think of the internet, you're not able to determine you're not sure which way the data packet goes to one computer to the next one. You must have a special cable then. So you must be sure that it's always the same time in it, and no deviation, no uncertainty in it.
Yes, I have a general question about multistatic operation. Is it possible to compare multistatic operation by, let's say, I have n or multiple monostatic radars, and I combine the output of the monostatic radars, their output, their individual operation, somehow. I do some information fusion. And is it possible to compare the performance of multistatic operation with n monostatic radars, or does it make sense?
Sure, makes sense. If you make a data fusion with a monostatic network with monostatic systems, your system will definitely.
What is the advantage of multistatic system in comparison to the other classical systems?
You will see your target on a different angle of view, so you have a chance to see it, especially if you think of a stealth target, you will be able to see it. If you have different or more than one bistatic pair, they will always show a Doppler shift to one bistatic pair. So the robustness of the signal will increase. If you're only working with a passive system, passive receiver, no one will know that there is a receiver node. That's an advantage. And let's say if you are transmitting, have one transmitter and two receiver, it's more efficient to use reflected signals by two receivers.
But what I have in mind was, assume that I have monostatic systems that are very much separated from each other. So they are seeing the target from different angles.
Yes.
And they are communicating with each other. So it's like a network radar.
Yes.
But they see targets from different angles, so they have some diversity, etc. They have those advantages, and they don't have the synchronization problem. Because they are monostatic.
Not so high.
Yeah.
You're doing it on track fusion.
Exactly.
So that's maybe a second. Sure. Can do it in this way. Will also help, definitely.
Definitely. Okay. Thank you very much.
Okay. Then I thank you. I forgot. I have so many papers. Just one. This would be very good if you, at the end of the day, fill out this questionnaire to give neighbor a feedback. Just to mention it again. So, would be very nice.